Today's lesson's over section 4.6. This section's over optimization problems. Now these are very similar to related rate problems in the sense that they're word problems. We'll be taking the derivative. But yet we're going to be looking at how we can maximize or minimize different formulas based on the information that we're given. So I have a 6-step process that we kind of go through. First one, obviously, understand the problem, read it, figure out what we know, what we need to know. 2, draw a diagram if that's possible, or if you feel like it's necessary. 3, we want to introduce any notation, identifying whether the quantity is maximized or minimized. Step 4, we want to write our equation with our given variables. We'll probably have a second equation involved because step 5, we're going to rewrite the function so it's one variable. So that's where the second equation or formula is going to come into play. And then number 6, we're going to look for the absolute extrema because that's where it's going to be minimized or maximized. And we're going to use the closed interval method to help us do that. Okay, so example 1 says a food company sells its beans in a cylindrical cans, which must have a volume of 20 centimeters cubed. What dimensions would minimize the amount of aluminum needed? So here, obviously has a radius of r, height of h. Now they do give us the volume of this cylinder, which is 20 centimeters cubed. So I'm going to plug that in, and that allows me to kind of find or isolate one of the variables, because I need to have another equation that has those same variables in common, which in this case would be the area. So the area of the outside would be 2 pi r, because that's the circumference, times h, plus the 2 circles that are on top and the bottom, so 2 pi r squared. And so since it has an h in common, I can take the h that I solved for in the first formula and plug it in, and that allows me to have a formula where I just have r. Okay, that's what we're kind of looking for with these, because you can't really, like, yes, we have tools to help us differentiate when we have two variables, but here they're not giving us enough information like we did in related rates to be able to find both of those or kind of plug things in. And so we kind of have to use both equations at the same time to make it so it's just one variable, and that allows me to use my closed interval method to help me find where it's maximized, where it's minimized, depending on the problem. So for this problem, we plugged in what h was. I found my area formula with just r included. Notice that I manipulated it so I could take the derivative of it a lot easier. And so I moved the r squared down so that I could solve. Now that creates an asymptote, so that is a critical number there at when r is equal to 0, but it's not going to be a real value because when I plug that in for the height, it's not really possible. Okay, but then I am able to solve for the numerator, which allows me to get the cube root of 10 divided by pi. And so what I want to do is use my intervals, and so I plug in or look at 0 and the cube root of 10 divided by pi. I pick values on either side, so I can pick the value of 1 and plug it in, and I can also plug in the value of 2. And notice that for in between 0 and the cube root of 10 divided by pi, it's negative. So it's decreasing there. Plugging in 2 gets me a value of 15.1. So it's increasing. So that means that it is a minimum at that cube root of 10 divided by pi. And so that's where our volume would be minimized. So I would plug that in, so I can figure out what my heights would be, because it's asking for the dimensions, so it wants to know my answer as the radius by the height in this case. So the radius would be the cube root of 10 divided by pi, and the height would be 20 divided by the cube root of 100 divided by pi squared. Okay. Example 2 says a farmer has 2,400 feet of fencing and wishes to fence off a rectangular field which adjoins a neighbor's field already fenced. Find the dimensions in the field, which maximizes the area. So here, because they told us the amount of fencing, that's kind of like talking like the perimeter. So that would be 2x plus y equals 2,400, because that fourth side is already fenced, so we don't need to fence it. I isolated y for that. Now, since we're talking about area or maximizing area, That's the other formula. So I'm able to say, oh, y is this, so I can plug it in, and I can manipulate my area formula, so it's 2400x minus 2x squared. I can take the derivative of that. That allows me to find that x is 600. And so then I'm going to pick values to figure out if 600 is a max or a minimum. And so plugging in the value of 1 gets me 2,396, and which is a positive number. So it's increasing in between there. Plugging in 700 will get me negative 400 for from 600 to infinity. So that shows that 600 is a maximum. And so then I'm going to plug that in back into the equation where I had y. So I can figure out what y is. So my dimensions of this field will be 600 feet by 1200 feet to maximize that area. Okay, example 3. A manufacturer wishes to package its product in a rectangular prism with a square top. If the material for the top and the bottom is 5 cents per square foot, and for the sides is 2 cents per square foot, find the dimensions to use to minimize the cost of the package with a volume of 2 feet cubed. Okay, so here they kind of talk about area, they talk about volume, and so there's a volume equation which will be x squared times y. Area will be 4xy plus 2x squared. So I first find what y would be with consideration to the volume, because they gave me what the total volume was. So it'd be 2 over x squared. I'll take that and plug that into the area formula, which gets me 8 over x plus 2x squared. Now I need to kind of alter this one because we're talking about cost, or minimizing the cost, not the area. So I'm going to adjust my area formula to fit in the cost. And so the top and the bottom is worth 5 cents per square foot. So the 2x squared is representing the top and the bottom. So I'm going to multiply that by 0.05. And then the sides are worth 0.02 per square foot. So I'm going to multiply the 8 divided by x by that number because they're representing the sides. And so now I have altered it from an area formula to a cost function. And so then that's what I take my derivative to help me find my critical numbers. Same like the last one, I get an x squared at the denominator, so that's an asymptote. So that's one of our critical numbers, even though it won't really be a value that we'll have, but it kind of constrains our area. I'm able to find the other critical number to be the cube root of 0.8. If you want to make that a decimal and get rid of the cube root, that is totally fine. I kind of try to keep it as exact as possible till the very end. And so I picked 0.5 and 1 to figure out where my values are. And when I plug in 0.5, that gives me negative 0.54, so that means it's decreasing at that point. When I plug in 1, I'm able to get the value of 0.04, which is positive, so it's increasing there. So that means that is a minimum. And so then I'm going to plug in my cube root of 0.8 into my formula that I set up for y. And then I can figure out that the y, or the height, is going to be 2.32 feet. And the sides, the side lengths are going to be 0.93 feet. And so there's my dimensions. Okay, have fun.